Alright, my name is Bianca, and this is my actual second rough draft for resting potential and action potential. So we'll start off with my clay models, and this is supposed to be a neuron, and I just wanted to symbolize that the neuron has these large particles on it, which are large organic anions. And the anions make the inside of the neuron negatively charged, even though there are positive ions on the molecule. The negative anions are the majority of the ionic kind of relativity. So they are negative, and they make the inside of the neuron negative, so the outside is all charged positively. So then we'll jump from that to over here. As you can see, a lot is kind of going on. So this is supposed to be kind of one membrane lines, and you'll see different particles on the top and different particles on the bottom. But first we're going to talk about the different particles. So we have potassium on the bottom. These are going to be represented by the long molecules there. And we also have sodium and chlorine on the top. Now you will see other particles in areas that they wouldn't normally be. That's because particles will diffuse to different areas. So this bottom part is inside the cell, and this is outside the cell. And another way to say that is the intracellular space is inside the cell, the fluid that's going inside the cell, and the extracellular space, which is outside the cell. So what I'm going to talk about now is the ion channels. So ion channels, there's sodium and potassium and chlorine, and they kind of let the particles go in and out of the cell, which is caused by diffusion. So diffusion is when you see potassium, the majority of potassium is at the inside of the cell, but you'll see some particles that are outside of the cell, and that's because diffusion's when a molecule wants to move from a high concentration to a low concentration, and that goes for each molecule individually: potassium, chlorine, and sodium. So what we want to look at is the sodium transporter and potassium transporter. So it's the sodium potassium transporter, and that's what I made this guy here. And it's a special protein that will only allow sodium to go out of the cell and potassium to come back in. So sodium, which they say 3 sodiums, so we'll pretend this guy's down here. So 3 sodiums will go in here and then be transported out, and then 2 potassiums, so we'll say one was up here, 2 potassium will come back in. So that mechanism is guided by ATP, so a type of energy, and the reason that happens is we need a lot of energy to keep the neuron in its resting potential. So even though it's resting, it still uses a lot of energy. So the last thing we'll talk about is also the forces of charge. So the forces of charge are, so the inside of the cell is very positive, and the outside is, or I'm sorry, the inside of the cell is very negative, like we said over here. But the outside of the cell is positive. So what happens is the negative particles of chlorine are being pushed outwards because they don't attract. They are not attracted to each other. However, the positive particles are attracted to the negativity. So like sodium wants to come in to the cell because it's positive. So that's where electrostatic pressure comes in. So electrostatic pressure pushes chlorine outside because inside is negatively charged. And opposite, sodium wants to come inside because it's positively charged, and the inside of the cell is negatively charged. And then I'm still working on action potential, which I'm having some difficulties explaining. But action potential, so that's when there's a temporary disturbance in the charge across the axon. So the charges, from what I'm understanding, are not the way they're supposed to be. And this graph kind of explains that. So from what I'm understanding, I'm trying to figure out if I should do this with a clay model also. But what I understand is two kind of nodes were placed onto a neuron, and if they gave, a minor zap, not much would happen, and then they would add a little more, not much, a little more, not much, and then all of a sudden on the fourth try, which is shown here in this graph, so this fourth try is right up there, the threshold of excitation was met. So even though it just kind of hit the perfect spot to be the threshold of excitation. And that's the value of the membrane potential that must be reached to produce an action potential. So in action potential, sodium ions flood. So I guess that was sodium. We wanted these white ones. So sodium ions are kind of in the place they shouldn't have been, and that's because of those ionic passages that are passive. So when this guy is being excited by the stimulation, these passages open up and sodium flows into here. And so I believe those are tied to the voltage gated ion channels. So when that stimulation happens, that's what that is. And I'll have to figure out how to make a clay model of the myelin sheath and explaining how that electrical conduction works in that way. And I think we also need nodes of Ranvier, I think I said it right, rate law, and the all or nothing law, and lastly, solitary conduction. So we'll have to figure out how to put that in a clay model, but this is my second rough draft for now. Thank you.